Good morning. Professor Arul Lakshminarayanan is a professor in the Department of Physics at IITM. He's a theoretical physicist whose main research interests are in dynamical systems, quantum information, many-body physics, thermalization, random matrix theory and its applications. He is currently working on quantum chaos, quantum information theory, chaos and transport, and mathematical physics. We welcome you, sir. Looking forward to your lecture.
Hello. So you're enjoying the summer? Or whatever we have to offer here. Thanks. Okay, good. So, excellent. So I thought I'll talk something which I have been subjecting to kids for a while, and but it's been some time. There was COVID and all that, and afterwards I have also not been participating in this. So one of the main themes which I think we are confronted with when we do science is that science is somehow creating, its order out of mystery, right? We don't know something, and then we do science, and then we know something. And so there are all these laws. So the laws, when we say law, we think about some structure, and therefore we think that there is this God-given or whatever nature-given idea that we can predict things based on these laws. Otherwise, the laws will not be of very much use. So you've studied in physics Newton's laws and various other laws from electromagnetism and so on, electricity, fluid flows, so mechanics, and then later on you may study quantum mechanics or other things which are describing laws connected to the atomic world and subatomic world. So, but in all of these things, it seems like if you think about it a bit, it's a bit of a mystery then Why are so many things appearing to be completely random? Isn't that the case? What do you think? Like, there are so many things. Like, for instance, you toss a coin, right? There are only two possibilities, head and tail. But we seem to be at a loss. You ask the most well-known PhD or professor, Nobel laureate, what have you, what will be the result of a coin toss? Most likely they are going to be correct only how many times? 50% of the time they are going to be correct. 50% of the time wrong, and there's no division between me and that. There's no difference between me and that exalted person. Both of us are going to be correct the same number of times. Why? Any guesses? Equally likely. But that's just restating what is being said in the book, that 50%. By the way, have you already done something called probability in your courses? So the first thing they'll say is, you have a coin, you toss it, 50% of the time you'll get head. Where is it written? Did the coin get manufactured like that? And shouldn't Newton's laws be applicable to this? It's a particle, you're giving it some energy. It's an object, its moment of inertia and various other things. You should be able to apply the laws of physics and find out whether it's head or tail. Yes, please.
The initial conditions are too chaotic. There's too many factors we have to consider.
Like
so while
what?
it's like air resistance or friction or exactly how much force you're imparting when you flip the coin.
Why is it that? So air, you said, let's parse what you said. Air friction. Air, did you say what?
Air resistance and
Air
friction
resistance.
from your fingers.
So if I was to toss this coin up in vacuum, I remove the air. Will it be more predictable?
You still have to predict the exact mechanics of your finger when it flips.
Yeah, why not? I mean, see, okay, if you object to my finger, you can have also a machine. Like, for example, you guys know the pinball machine. I don't know whether you know that, but it's some kind of arcade game, right? So, there are so many things which you can predict. I mean, your finger is not that random an object, right? You guys have played marbles or carom and so on. It seems fairly, you can predict things. Yeah.
Sir, it also has to do with what face the coin is facing while you toss it. So if you know that, and
Yeah, you know that. Here, I give you this coin. You know everything. Can you predict? So I know, yeah. So here is this. Let's call that head. Then?
yeah, I mean, like if you're in a vacuum and there's no other factors influencing the coin toss, your finger is completely consistent and you know which face you're tossing it, it should be possible to predict.
All the cricket games, there seems to be a very critical thing. I'm sure that the IPL would have figured it out by now, if there is something to be figured out. Yes.
Sir, it's that you can't predict exactly using the position and movement of your finger, because even one slight micrometer kind of deviation
Why?
in the
Why do
position
you
of your
say
hand.
that? Why do you say that? I mean, is that some law that micrometer deviation is going to give it a problem?
No, sir.
Why is it that sensitive, you think? Yeah.
Sir, it may decide the number of times the coin could flip in air, and maybe through the number of flips we can find out what is the end result.
So, I mean, you're all very hopeful. I like that. You're optimistic. You're saying that, look, there's nothing wrong with physics. Don't need to panic. It's just that we don't know the initial conditions too well. We have to know micrometers. We need to analyze it better. And actually, I agree with all of that. Yet, this is the very essence of probability theory. I mean, the probability example at least, that there's 50% chance. This is just, one of the things where there is chance. Why is there chance? Games of chance. All of these, there is, why should there be probability at all? Shouldn't there be only physics and no probability? Right? So, how does, if you think about the weather, for instance, we can't predict the weather too well. In fact, probably only with 50%, we can't, well, you might as well say sometimes it may rain, it may not rain. It looks like it's a 50% probability. So it looks like the weather is also something which is, at least the short-term weather predictions look pretty chancy. And it's not because, again, we don't know the laws behind it. We know everything, we know a lot about how fluids behave. And yet the weather is still kind of a mystery to us. So any other phenomena which you think is appearing to be random, which we see around us? Disasters, yeah, earthquake, for example. This is something which, again, it seems to be so much research and effort has gone into that, but to say, and people know quite well how or why earthquakes are occurring, yet it seems very difficult to predict when the next earthquake is going to occur. Yeah?
So like when you have a bowl of water and you're putting a drop of ink into it, the way it dissipates is completely random.
It dissipates.
Yeah, the way the ink just spreads through the water.
Yes. Well, it doesn't dissipate, mixes.
It mixes. The way it mixes is random.
It mixes. You are saying that if I drop the same, I'll try to drop exactly at the same place, the exact same drop of water in the sense of the size and shape. If the future of that drop might appear to be quite different. Indeed, but the final state is the same. Final state is predictable. What is that final state? Yeah, it's just uniform, it's mixed up. The ink drop is mixed up in the water. And in fact, let's say that you have dropped a small volume V of ink into a big V volume of water. What will be the fraction of ink in any segment of water? Small v by capital V. We are using our kind of common sense saying that it is uniformly mixed, right? So that seems to be predictable. The final state is kind of a thing where there are as many ink, although there's no ink that's created. It's the same amount of ink molecules, but it seems to have spread out in that volume of water. Any other examples?
So genetics, how the baby born, whether it's a girl or a boy, or how she or he looks.
Yeah.
That is not predictable.
So now you've gone beyond my ken of knowledge, but I'm sure that is the case. And so biology holds a lot of uncertainty even when we wake up, right? You monitor your times, you're not waking up at exactly the same time. Maybe your mom is waking you up and she's probably waking you up, or you keep an alarm clock. But we have rhythms. The human body has so-called circadian rhythms, right? There are actually clocks. And there are oscillations in these things. So we are also oscillators of some kind. But clearly, it's not a perfect oscillation. Any other examples? Yeah.
So quantum mechanics.
What about it?
No, quantum mechanics, it's random.
It may be, but I'm asking for examples in our common experience. Quantum mechanics is a subject in which, or it's a theory, in which in fact randomness is fundamental. You're correct. But I'm asking for phenomena around us that we see and experience, where there seems to be apparent randomness, like a coin toss kind of randomness. Actually, it's all around us, right? You go to Chennai roads and Nothing is predictable. Can you predict when there's a person going to come and, so in fact, what about music? You think music is something predictable? Only if you know it. But then if you know it, there's nothing to predict. If you don't know it, is music something which is random? We'll usually call that noise. If I sing, it will be random, but not if somebody who knows music is singing. At the same time, it's not what we think about as periodic. So what is the opposite of random? Can you tell me? What in your view is the opposite of random? Periodic, ordered, you're giving, arranged. Yeah, okay, but predictable, but still, you might have something which is predictable but appearing random. But we may be thinking of periodic as opposed to random, as the opposite of random. It may be not, it's not really true, but let's say that is the case. Then music cannot be periodic. If music was periodic, that's completely boring, it will put you to sleep, right? So music is some kind of a balance, I believe, between randomness and periodicity, so that you don't fall asleep and you enjoy it, right? But can you tell me from your experience of, let's say, maybe also from what you have studied in mathematics, can you tell me something which appears to be random but which you can actually predict? Which you can calculate or predict? Yeah.
So like the digits of pi.
Very good. So, I know a few digits. How many digits do you know?
Sir?
How many digits of pi do you know?
Any given arbitrary number of
No.
digits.
How many do you know? Any number?
Me.
I can't.
Me, sir?
Yes, you as a human being.
50.
How many do you know? Hey, just tell the value of pi, man. You only told me.
I don't know the exact value, sir.
Yes. Nobody knows. But tell me approximate value.
Okay, sir. 3.141592653589.
Oh, very nice. So, look, I don't know whether you're fibbing, okay? Because beyond 3.14159, I can't say whether it is. But I'll agree that that is looking actually as something which is random. Suppose somebody did not tell you that those were digits of pi, and he is just reciting this. How will you figure out whether it's random or not? In fact, you can do this experiment. You take digits of pi, million digits of pi. On a computer today, you can get this in no time. In fact, you can get much more than a million. And you see how many times the digit 1 is occurring. How many times 0 is occurring? There are 10 possibilities, right? In the decimal expansion of this. How many times do you think? How many times will the 0 occur? 1 occur. So, because, then they will teach you in probability that the probability of 0 appearing in pi is how much? 1 by 10, because there are 10 possible digits. Is it true? So, why not? How do you know? You did the experiment? Sorry? Louder. Infinite. I know, but even coin toss you can't do infinite, no? So, but you believe that it is half. Equally likely, yeah. So we can't consider getting digits from 0 to 9 of equal probability. So we cannot say that number of total number of units to be equal. Right. You cannot. In fact, you can ask even more bigger question. Actually, there's a chalk, right? So let's write 3.14159. Hey, what did you say after that? 26? I don't know. Let's say something like that. Okay. So ignore this dot. We will include all of them, or it doesn't matter. That's just one digit, and it will hardly matter to them. So let's include all of these things, and then we are asking what is the frequency with which 1 is appearing, what is the frequency at which 2 is appearing, and so on. It may seem to us, without, suppose we are to guess that this is actually like a random thing, we might guess that the probability of each of them occurring is 1 by 10. Maybe. Now, let's also ask the following question. Let's take things like 14, 41, 15, 59. Okay, so that is, instead of just asking for how many times one digit is occurring, I'll ask how many times are 2 digits. How many times is 14 occurring here? Huh? 1 by? Louder. 1 by 100. Because there are 100 possible. Huh? So is this true? So actually, I think this is true. Check it out. Okay. So a number is called a normal number if this is true. And actually there are deep questions about normal numbers. A normal number has in its decimal expansion, let's call it a decimal expansion, but it need not be only decimal. The base should not matter. The decimal expansion, you have all the possible strings are occurring equally likely. That seems quite a remarkable fact, but there is nothing mysterious or random about, well, there is something mysterious, but nothing random about pi for sure. And there are other numbers, so this is actually an irrational number. What else can you say about it? Huh? What does that mean? Huh? Transcendental is what? Not a solution of an algebraic equation. Unlike maybe square root of 2, which solves this equation. So it's an algebraic equation with only integer coefficients, and it's a square root of 2. Square root of 2 also appears to be pretty random. 1.14. So this also appears to be the case, and here also maybe things will appear to be random to us. But what is square root of 2? What is random about it? Therefore, my first point is that there may be something which is appearing to be random, and it might follow all these laws of probability even, but at the same time it may have behind it something very simple. Okay. Another example from our everyday life is we play so many games. All these games are governed by laws, but we keep playing these games over and over again because there's so much variety which is developing from those simple laws. Take the game of chess, for example. It's a finite game, finite rules, but we are playing it for centuries, and it still continues to be a very interesting game which we can't really predict what's happening after some number of moves. Yeah. Primes, yes, what about it? Yeah, so the prime numbers 2, 3, 5, 7, 11, etc. There's no formula for it. There doesn't appear to be a, and they are the atoms of arithmetic. So the prime numbers also is an example, is a prime example, if you wish, of something which appears to be random. In fact, let me go on from maybe in my talk after this introduction, so that we will see. So what I will do is come to the physics in the second half of my talk. I will deal more with simple mathematics, what looks like simple mathematics, but which is quite deep. So this is the simplest sequence probably one can think of. And if I ask you what is the next number, every one of you will say 8. Okay, and then you will say that you can predict it. But of course, I can be vicious and have some other number at the end of it. But let's say that that's the sequence n plus n is the nth element. So it's just a collection of integers from 1. Now, this is something where the difference is the same. The difference between two consecutive numbers is the same and it's equal to 1. So what kind of a sequence is it? Arithmetic sequence. So an arithmetic sequence, and in physics we come across such a thing, for example, in free motion. You have a particle moving with constant velocity. Its position is going to be velocity into time. So if you look at the sequence for a fixed speed or velocity v, if you look at it in time, from time t to t plus some delta t, let's say that every 1 second you're monitoring it, it changes by v. Okay, so in fact that looks like constant motion, and if you plot the position versus velocity, position versus time, you will get a straight line with a slope that is the velocity. Okay, so this kind of arithmetic relation is here. The next is this sequence, which is just the square of these integers on top, and you will say that the next one is 36. And you may be right. And if you ask what is the sequence here going to be given as, so the first sequence is just going to be given by n, the nth term of this is just n, and the second one it's just n squared. And this quadratic growth or geometric growth is going to be given by n squared. And in physics you will see that, for example, in this constant position with a constant acceleration rather than a constant velocity, we know that it's growing quadratically. We'll say that it's growing quadratically. Okay, so, and if you look at these two numbers, these two simple sequences here, and ask how many numbers are less than a given number x. Okay, so suppose you're given x and ask how many elements of the sequence are less than x, then the answer is very clear. The number is x itself, right? Like there are 7 numbers less than or equal to 7, 8 numbers less than or equal to 8. What is the answer here? If you were to ask how many sequences, how many numbers are there in the sequence less than a given number x? Huh? Square root, right? Square root of x. Like 25, if you take square root, there are 5 entries less than that. 16 less than, okay? So indeed, that you say that n of x is the number of terms less than x is growing as square root of x. So this is x, the square root of x. So somebody, so like, okay, let's also see this very beautiful formulas. So the sequence 1 by so 2, 3, 4, etc. Let's take the inverse of them. Let's take the reciprocals. 1 by 2, 1 by 3, 1 by 4. It's a decreasing sequence. Let's say that we add them all together. It turns out that this does not lead to a finite number. As you keep adding an infinity of them, this will grow, diverge and be equal to infinity. So there is a difference between these two sequences in the sense that if we take a sum of 1 over n equals 1 to infinity, this is infinite. But if you take the second sequence, which is just coming from squaring these elements, and you take 1 by 2 square, it's a very beautiful formula, and that gives you pi square by 6. It's attributed to Euler in 1735. It has a long history, and it's connected to very important things, including the development of calculus and so on. So you see, the appearance of pi seems, in this case, although we said that pi is so random and all those digits we can't predict, you may look at this formula and say, what's not predictable about it? All I have to do is going on adding 1 by 2 square, 1 by 3 square, I can predict that. So all these digits which appeared random to us, actually they are coming from quite simple laws here. I mean, in a way, because I can go on adding this, multiply by 6, also there's no mystery in 6, take a square root, I will get pi. These will give you rational approximations to pi. Well, actually not, it will give you rational approximation pi square in this case. Okay. But you also know an infinite series for pi. Do you know an infinite series for pi itself rather than pi square? Have you guys studied expansions like these? Not yet, I guess. Like tan inverse x. You don't know how that series goes. Okay, good. So, things to learn. But this is a beautiful formula. It actually converges. It's converging. So this thing is smaller than this. This is also smaller than this, and so on. It's sufficiently small enough that you're adding an infinity of them. It converges to pi square by 6. There was a question or comment.
Sir, I had it out in the previous slide, sir.
Yeah.
You said it's number of terms less than x should be x, sir. Shouldn't it be x minus 1 by any chance?
Say that again, louder.
Shouldn't it be x minus 1, sir?
X minus 1, number of terms less than x. You are correct. So, number of terms, so you're saying that less than 4 should be only 1, 2 and 3. So, you can say less than or equal to. Okay, it doesn't really matter. So, this x or x minus 1, and also, like for instance, you may not include even this, an integer. You can ask how many terms are there less than, for example, 4.5. Okay, and then you have to take the integer value of that. So, to be very precise, then you might say that less than or equal to that is some kind of what is called the floor function of that x. The nearest integer less than or equal to that. Okay. So indeed you're correct. But I've been sloppy in this slide also because actually we'll be interested in what happens to this n of x as x is very large. So this minus 1 and so on doesn't really matter much to us. But good point. Anything else? Alright. So there is this prime numbers which was mentioned as an example of something which is random, in the sense that we don't have a formula for this. What is the number of prime numbers less than x? The same question which we asked for this simple sequences, we can ask for this complicated sequence. What is the number of prime numbers less than a given number x? In this case, there is no simple answer like x or square root of x, but there is this beautiful formula that it is going as x divided by log x. So it's clearly not going to be x itself, correct? It can't be x because x is the number of all integers are growing at x. So it has to be less than x. The number of elements has to be less than x. But it's also not that slow. It's not as slow as square root of x. Right? So it's much more frequent than the squares. So actually there is this mysterious thing that it's actually x divided by log x. And this again, if you count exactly and then you tell me, well, this is not even an integer. So what are you saying about? So that is where this symbol tilde comes. These are asymptotic. So it means that for large x, this n of x multiplied by log x divided by x will be tending towards 1 as x tends to infinity. So these are called asymptotic formulas. And so this is known as the prime number theorem. And a lot of mathematics was devoted to actually proving this prime number theorem from Hadamard, Riemann, and a lot of 19th century physicists. Mathematicians. So now we looked at what happens. We looked at what happens to 1 plus 1 by 2 square, etc. And then we said that that's equal to pi square. By 6. In fact, you can go ahead and find things like 1 by 2 power 4, 1 by 3 power 4 and so on. That will be some pi to the power of 4 and divided by something. And then if you ask what is 1 by 2 cube, 1 by 3 cube, this also will converge because each of these things is smaller than this, but actually I don't have a simple answer for that. We have a simple answer for this. We have simple answers only for these being integers, even integers. Okay, so let's put an s there. If s is an even integer like 2, 4, etc., it's some pi to the power of s divided by something, multiplied by some rational number, but otherwise this function is a very interesting function and is actually called the Riemann zeta function. So that's equal to sigma 1 over n to the power of s. S is 1 to infinity. So it's named after this famous mathematician Riemann, and it's called a zeta function because of this Greek letter which is used to denote that. So it's a function of what? It's a function of this power to which these reciprocals are raised, this power s. And there is this beautiful formula which is connecting these two prime numbers, and it's called the Euler product formula. It says that this sum, an infinite sum over the integers 1 over n to the power of s, is a product over all the prime numbers p. So 2, 3, 5, 7, 11, etc. of this reciprocal 1 by product 1 by 1 minus 1 by p to the power of s. Product over all the primes p. So that is the zeta function as well. So you should be able to prove that if you know the binomial theorem. So I leave it as a challenge to you, those of you who don't know this. But it's a very interesting fact that there is an infinite sum over all the integers. This is a product over the primes. This is a structure which is there. And this is where the genius of Riemann comes in. You see, so this is also a Riemann zeta function with s equal to 1, right? This is the power s equal to 1. So s equal to 1 does not converge and is going to infinity. So Riemann asked, can we generalize this function to all values of s, not just integers, not just positive integers, but to all numbers, in fact all complex numbers. And Riemann showed that that can be done through a process which is called analytic continuation. So there is a beautiful function. So this function makes sense as a convergent one only if the real part of S is a complex number now, real part of S is larger than 1, it converges to a number. But if the real part of S is less than 1, is equal to 1, it is equal to 0. But if it is less than 1 also, it makes sense. In fact, it can be complex numbers and it makes sense. It will give you some complex number at the end of this. That's called the Riemann zeta function. Why is this interesting? Before I go on to say why it is interesting, actually Riemann studied this in order to prove this formula. In order to prove that the number of primes is growing as x divided by log x. And he wanted to find a formula for prime numbers, which seems impossible. But in fact, he showed that if you studied this zeta function, it contains in it all the properties of prime numbers because of this Euler product formula. So there's a close connection between the zeta function and prime numbers. And there is something called the Riemann conjecture. How many of you here have already heard about it? The Riemann conjecture? No? That's surprising because there's a lot of money involved in it. Huh? Sorry? Millennium Prize, yeah. So, but of course it's difficult. A lot of people try to show this. So a conjecture is something which is a guess of a serious kind, which mathematicians put forward, or sometimes scientists put forward in general, and they are not sure about. And the Riemann conjecture is the following. It said that let's look at the the zeta function values of the zeta function. It can actually go to 0 as well. This function, it doesn't look like it can go to 0, but if this S is continued beyond into the all values, all complex values, it is possible that for some values of S, these Si, let's say, the zeta function is equal to 0. The zeros of the Riemann zeta function. You see, sometimes it's kind of strange that why should zeros be important? Let's ask ourselves this question. Suppose somebody gives you a function. Why should the zeros be important? It looks like the most unimportant thing are going to be the zeros. It's vanishing. But in fact, they're very important. Can any guesses from what you already know? Let's just think, yeah. Huh? Yes. Factor, what do you mean? Let's just take a simple case. Let's take a quadratic equation. So let's take a quadratic equation, okay? Quadratic equation has how many zeros?
2. If ABC are 0, then infinite.
Huh? 2 zeros. If you know the zeros, do you know the quadratic function? Quadratic equation?
Yes.
You know that. So actually, zeros control the whole thing, right? So the product of that, so just x minus a, x minus b, maybe multiplied by some constant. That constant you don't know maybe, but once you know these a and b are the roots of this quadratic equation, the quadratic equation is simply x minus a into x minus b. It's proportional to that up to a constant. And therefore you know that. So the roots determine the function. So actually there's a lot of information in the humble zeros. And the Riemann zeta zeros are like that. It's a very complicated function, but the zeros contain paramount importance, and in fact all the distribution of prime numbers and so on is written exclusively in terms of the zeros of this zeta function. Where are these zeros? And this is where the conjecture is, Riemann conjecture, that all of them are in the line S, real part of S equals half. So he conjectured that the ith Riemann zero is of the form half plus some I times maybe xi, where this xi is a real number. That is, the real part of the zeros have to be half. There are only a discrete set of them. It's not as if all the points on this real part equals half are zeros. So what are these? These are the marked zeros of this. Okay. There are some zeros here in these negative integers, but they are not considered to be important. -2 and -4 and so on. They are considered to be trivial for some reason. So the non-trivial important zeros are coming from this here. And you see they are all aligned here. So there is some order in this kind of a mess that these zeros all have this. So this is the conjecture. The Riemann conjecture states that the zeros of the zeta function have this form and they lie on this line. Nobody has proved this so far. If you prove it, you're a millionaire overnight. Now, there have been many attempts, many failed attempts. If you see this thing, there was even maybe 4 or 5 years ago, there was an Indian mathematician who claimed that, so they've solved it. There was actually, he also died. He died. There was a very famous mathematician from the UK who also claimed that he had solved it, but unfortunately, it does not appear to be the case. But what is interesting about these things is that these xi values, which then determine this, appear again to be random. So the randomness of the prime numbers seems to be taken up by these Riemann zeta zeros. You can see that there is a reflection symmetry. If there is an xi, there is a minus xi. So we can just concentrate on what's there above this and look at this. So people have calculated actually billions of Riemann zeta zeros, billions, using very sophisticated numerical techniques, and they have found that they all satisfy this conjecture. So there is no violation to the conjecture. People have also proved that there are infinity of zeros on this what's called critical line, but still no one has actually shown that this is true. So here is a simple function whose behavior is completely determined by this set of numbers and the set of real numbers now, this xi. So x1, x2, x3. These are the Riemann zeta zeros. And there is a very curious connection which was found about 20-30 years back to physics, when they found that if you look at these gaps, we looked at gaps of these natural numbers, all the gaps were equal, arithmetic sequence. Now you can look at the gaps of the Riemann zeta zeros and ask, how are they? How does it look? How is it distributed? What is the probability that a gap will be so much and so on? And they found that these were exactly like the allowed energies of quantum systems. So there is some connection to quantum physics, to quantum systems, and very particular kind of quantum systems which display unpredictable or chaotic behavior. I'll come in my second half of my talk to chaos. So they found that there is a connection between this Riemann zeta function and this. So there is a lot of open questions. By the way, those of you who want to play with the zeros, these zeros are available, many zeros you can download, and then you can play with them. You can do a lot of analysis on that. I think it's time for me to stop, or how much time? It's 55, right? I think I should stop here. Maybe I'll resume after 10 minutes. Is that correct? All of you are eager not to break. Okay, if you are eager not to break, maybe I will go through this one thing. See, what I want to show is this following. The Riemann zeta function is this zeta of S. 1 by the Riemann zeta function is very remarkably, it can be written again, it looks like that of 1 by n power s, except that there are some integers here, mu of n, which can be 0 or plus minus 1, depending on n. And you see, of course, 1 by, zeta of s I wrote down there, so 1 over that is simply the product of these prime numbers. Okay? What is this function mu of n? Mu of n is called a Mobius function, and this is how it looks. So n equals 1, 2, 3, 4, 5, 6. Look at this. 1, minus 1, minus 1, 0, minus 1, 1. Can you tell me what is the next one here? Huh? 0. How do you know? You'll be 1/3 chance correct. But how do you know? Is there some order in this? Just look at this sequence. It contains only 3 numbers, 0, plus or 1 or minus 1. I can't predict it. And here I have plotted this Mobius function as a function of n, and you can see that it seems to have a pretty random behavior. There is 0 or it's plus 1 or minus 1, but there's nothing periodic about it. There is nothing, it looks pretty random. Do you see that? And how do you construct this Mobius function? This is the thing. So you take a number n, you know the prime factorization. Every number has a prime factorization, p to the power of a1, p2 to the power of a2, pk to the power of ak. These are prime numbers, and it's a unique expansion. So the Mobius function of n will be equal to 0 if any one of these primes is repeated. That is, if any one of these a's is larger than 1. If any one of these powers is greater than 1, it's equal to 0. N has repeating prime factors. If it doesn't, that is, if all of them are like this, then it's minus 1 to the power of k, which is the number of distinct prime factors. So the Mobius function of 4 is 2 squared, so that's a repetition there, so it's 0. Mobius of 6 is 2 times 3, so there's no repetition there, it's minus 1 to the power of 2 is plus 1. That is the rule which you apply, and you see again, here is an example of a very simple deterministic law which is leading to something which looks random. And not only is looking random, it actually appears in very important functions such as the Riemann zeta function. Okay, I think I will stop here and we'll resume after 10 minutes. Are there any quick questions? All right, we'll come back.